This is the second video in our series on integrated rates. In this video, we will look at how to use the method of integrated rates to determine the rate law. There are two methods for determining the rate law experimentally. In a previous video about initial rates, we saw how to use the method of initial rates to determine the rate law for a reaction. In this video, we will be looking at the second method, the method of integrated rates. When we previously used the method of initial rates, we needed to run two experiments in order to be able to compare the effect of changing the concentration on the rate. In the integrated rate experiment, we only need to run one experiment, but we run it for a longer time period. Typically, these experiments are done using spectroscopy and Beer's law to convert absorbance to concentration. Once we have data of concentration versus time, we need to make three separate plots, usually using Excel. We'll first plot concentration versus time. We'll make a second plot of natural log of concentration versus time. And finally, a third plot of 1 over concentration versus time. We'll then compare these three plots to decide which is the most linear. The most linear graph will be the one that has the highest R-squared value when you do a trendline fit. The graph that is the most linear will be the one that determines the reaction order. Let's summarize these results. If a plot of concentration versus time is the most linear, we would say that the reaction is then zero order. On the other hand, if the natural log concentration versus time plot is most linear, our reaction is first order. And finally, when we compare the three plots, if the 1 over concentration versus time is the most linear plot, that means the reaction was second order. Finally, a small note about the experimental conditions under which this is run. We need to run it under conditions in which only one reactant is determining the rate. This is usually accomplished by using a large excess of any other reactants. The value of K that you determine in these types of experiments is then called a pseudo-rate constant, because it will contain the concentration of the other reacting species. Let's look at an example. The kinetics of the reaction of 2NOBr going to 2NO plus Br2 were studied experimentally at 10 degrees Celsius, and the concentration of NOBr versus time was collected. The following plots were then constructed in order to determine the rate law for the reaction. We have 1 over the concentration of NOBr versus time, concentration of NOBr versus time, and natural log of concentration versus time. Recall from the integrated rate equations that these correspond to 0, first, and second order plots. Comparing these plots, which one is the most linear? Well, clearly, the concentration versus time plot is not very linear. Both the first order and second order plots appear to be somewhat linear, but when we compare the R-squared values, we see that the second order plot is the most linear of the three. This means that our reaction is second order in the concentration of NOBr. How would we write the rate law for this reaction? So we have rate is equal to K. Since we decided it was second order, it'll be equal to the concentration of NOBr raised to the second power. What is the value of rate constant? If you go back to our table, we see that for this type of graph, the slope of our second order plot is equal to the value of K. So in this equation, we have K is equal to 0.07921, and the units for that are going to be concentration, in this case specifically molar, per second. In this video, we've shown how the integrated rates method can be used to determine the rate law and the rate constant for a chemical reaction. Watch the next video to talk about the concept of half-life.